Hey guys, just a little note on some analysis that I did trying to identify deep sky objects that are compatible with my complicated horizon. Now, my complicated horizon probably is not as complicated as many of you, but some of us aren't fortunate enough to live out on a prairie with field of view about 360 degrees from 0 to 90 degrees altitude. We have to live in a suburban or urban environment where we have some pretty serious restrictions on where we can see and what part of the sky we can see. So I underwent a little bit of a study here to try to find what DSO targets are available to me in particular. I did this because I was buying that cooled camera, which gave me the opportunity to do imaging year-round. Wasn't able to do that before with just a DSLR because of the heat. I bought the new telescope, the 714 millimeter focal length telescope, which gives me access to larger objects than my very high magnification SCT telescope. So now I have the opportunity to image year-round and to image a greater variety of targets, which begs the question, okay, what are the targets? And which ones can I see? Which ones can I see from my location on Earth? But then which ones can I see because of my horizon? And so that's what I wanted to share with you a little bit today, is some of the findings and some of the analysis I did to come up with the answer to that question. This is the beginning of the horizon, and this is the worst spot for me in the horizon. I found this app, Diopter app, for the Android. It's free. It's a good app. There are other ways of doing this. Certainly I've used Sky Safari on the iPad, which you can hold up and point towards a location, identify the azimuth and elevation. What is neat about the Diopter app is that you're taking a picture with your cell phone, so it's recording right there in the view what the azimuth is and what the corresponding altitude is. And that's not something you get with the iPad and the Sky Safari app I was using. But you can see I'm sitting in a chair in the backyard looking up behind me at the house. So this is essentially the view my telescope would have. And at this particular azimuth of 143 degrees, I can't see anything below about 37 degrees in altitude. Now, if I scan over a little bit to the right, continuing on around the circle, at 168 degrees, I can see a little bit better off at about 29 degrees. And then if I continue on down, now I'm looking at the houses down the street from me, and at 217 degrees azimuth, I'm basically at a 8 degrees altitude limit, which is fine. You wouldn't want to image below that anyway. And then, of course, as we come on around from 217 back to the north, we get along my fence, both here and the fence coming back to the north, and it's all at a pretty low altitude. I don't have many obstructions to the north. It's mostly to the south that I have the obstructions. But what is nice about this app is you can go ahead and snap these pictures, making the full circle around, and then you come up with a table of azimuth and altitude angles that you just copy in from these various numbers here in the pictures. And now you have a table that's totally compatible with, for example, Carte du Ciel. This line here, delineating the black sky with this brown region here, is that line that we just looked at, the altitude azimuth line. And Carte du Ciel is just coloring this in with a user-defined color. But it's nice to know when an object that you're waiting for is just below the edge of the house, and then when it's going to eventually poke up above the house. So it's nice to be able to track an object during an imaging session to see what's actually out there for you to sleuth to and expect to see something. After all, you don't want to spend a lot of imaging time taking pictures of the back of your house. But this is using the horizon in real time during an imaging session. I'm more interested right now in a predictive tool to help me identify targets that I had not previously thought of or heard of before. Now, there are websites and other tools out there, such as what was formerly DSO browser, but is now telescopius.com. I can type in an object such as M51, and it'll tell me for today when the object is going to be visible and what its maximum altitude is going to be, 76 degrees at 11 p.m., 11:40 p.m., transit north. That's all good and useful information, but once again, I already have to know to look for M51 in order to get this information. I'm wondering if there is some deep sky object, some NGC object, some Messier object out there that I just haven't thought of or haven't heard of that is actually visible from my location. That's what I'm after. Well, there are many star catalogs, deep space object catalogs, and I've perused through them and combined them into one catalog with a common format. They all have different formats. But here's a catalog that I created. It started off with about 5,000 entries, many of which I culled out fairly quickly just because of the type of object, the size of the object, the magnitude of the object, etc. But here's kind of a snapshot of what some of these objects look like in this particular list, which contains about 1,600 entries. Now, mind you, I don't know what any of these are. There's a few of them that I do know, but for the most part, I don't know what IC 5134 is, for example. I'll have to go look that up. But here, at any rate, we can see the object name. We can see its type, whether it's a galaxy, G, or nebula, N. We can see, if it's a galaxy, what the morphology is. For instance, I took out all elliptical galaxies. I'm not interested in taking pictures of elliptical galaxies. It's all that I can do to keep from turning my spiral galaxies into elliptical galaxies. So I'm not interested in taking pictures of those. So I only wanted to keep spiral galaxies in this list. Then we have the right ascension in decimal hours. We have declination in decimal degrees, the size of the object if it's available, and the magnitude of the object if it's available. Oftentimes you'll see zeros in here. It doesn't mean it's that bright. It's just that information was not available for that object from whatever catalog I got that from. So now the question is, given this list of 1,600 deep sky objects, which one of these can I actually see from my location and with my specific horizon? That's what I'm interested in here. Well, to do that, we got to go back and do some math. Now, I'm not going to drag you guys through all the math, but just to kind of give you an idea of how that I went about figuring this out, at least for myself. This is the Earth. We have the equator. The Earth is tilted by about 23.4 degrees relative to the plane, the orbital plane of the Earth. And we have a prime meridian. And on March 21st, the intersection of the prime meridian and the equator exactly falls between the Earth and the Sun. That's when we define our coordinate system for the location of our deep space objects. So from that instant in time, we define a coordinate system, XYZ coordinate system, and a deep space object is defined by its location in right ascension, which is the angle measured around the equator, not the Earth equator, the equator, and declination above or below the equatorial plane. And so also if you have the distance of the DSO. But in this particular calculation, the distance to the DSO is so large compared to any other distance you might be concerned about, the radius of the Earth or the Earth distance from the Earth to the Sun, that for all intents and purposes, the only distance that matters in these calculations is the distance to the deep sky object, which for all intents and purposes can be 1. Just call it 1. Now, let's take this coordinate system and step back a little bit. Because the distances between the Earth and the Sun don't matter, they're very small compared to the distance between the deep sky object and the Sun, or the deep sky object and the Earth, I'm just going to take the axes that I had at the center of the Earth and move them to the center of the Sun, so that now I can do a simulation of the Earth orbiting the Sun and rotating, of course, and at any given time during its 1 year traverse around the orbital path, I can determine where I am on the planet and what up is, and determine the corresponding vector to the Sun and the corresponding vector to the deep sky object. And of course, if my up vector is aligned with the vector to the Sun, then that means it's daytime. If they are in opposite directions, then it's nighttime. And if the up vector is parallel or has a component in the up direction that matches, that is in the same sign, SIGN sign, of the deep sky object, then that means I can see the deep sky object and it is dark. All right, so all I have to do now is just run this simulation, say at 5-minute intervals for the full year of the Earth going around, and I can track the position of the path of the deep sky object in altitude and horizon space, and also verify when it gets above the complex horizon that I recorded with the Diopter app. That's the objective. Now, we're not going to do all the math here, but here's what we get. We do lots of math, and what this will give me, this program that I wrote, what it's going to give me is essentially an updated version of this table here, but it'll throw out all the things that I can't possibly see. They're just below my horizon. Also, it's going to give me an observation list. Part of the observation list is a score. We'll talk a little bit more about that in a second. But it gives me an observing score on a daily basis. I will also get a day, month, time when the object is visible for more than 4 hours and reaches a peak altitude of 30 degrees. That's kind of the day when, if you're planning on taking pictures of that particular deep sky object, that's the day when you won't be wasting your time. You'll have 4 hours to observe it. It'll get up at least to 30 degrees above the horizon, and you might actually get some decent data. But it's just on the beginning of when it becomes visible to you. It's not the optimal time, certainly. The more optimal time is the day and month when the observation score reaches its maximum value. And again, we'll look at that a little more closely in a second. And for each object that I can see, I get a plot for all the days of the year of the altitude of the object, maximum and minimum altitude. Minimum altitude will be controlled in general by that complex horizon that I mentioned, that the house rises up in the south and blocks views and so on. But it will also give me the number of hours that the object is visible on that day. And then I can plot that throughout the year and use that for planning purposes in deciding which target to go after and when I should start going after that target. Okay, so here's the results of the analysis. I'm plotting the observing score for each observable deep sky object as a function of time of the year, so from January through December. The observing score is a product of two numbers. One is the number of hours that the target is visible during a given day, divided by 11 hours. So that number will be near 1, maybe slightly larger than 1 for a target that's visible for a long period of time. And then I'm multiplying that number times the maximum altitude that the target reaches, divided by 90 degrees, and that number will be less than 1, and 1 if the target passes right overhead. So the product of those two numbers should be around 1 for a target that's passes overhead, directly overhead or near overhead, and is observable for a long period of time. It can be slightly larger than 1, but for most cases, it's going to be limited by 1. Now, you notice here in this plot that the high observing scores tend to occur in the winter months, and then they fall off in the summer months and then increase back up as we move back into November and December. And that's just a reflection of the fact that in the Northern Hemisphere, we have longer nights during the winter. And so that gives us the opportunity to have observe a target for a longer period of time. Another thing we see here is that galaxies are much more easily observed in the January to May timeframe, which we'll call that galaxy season, and nebulas tend to be more common from July through December. So we have a preferential time of year that everybody's heard of before, the galaxy season, nebula season. And for me, there's this little dead period here between in June where no targets have a high observing score. Now, it doesn't mean the targets aren't visible. They are. They're just not reaching their peak time for observability. And in some cases, we have some very low observing scores, and we'll actually take a look at one of those in a moment. This is the output in terms of a file that the program spits out. I basically have the target name, the number of hours, maximum number of hours it was visible on a given day, and the maximum altitude that target reached on a given day. I have the imaging time, optimal, the initial imaging time when the target will be visible for at least 4 hours and at least reach an altitude of 30 degrees. That's what this first number is here. And then I have the optimal imaging time, which is the time when you would see the maximum observing time and the maximum altitude, and therefore get to the maximum observing score. So you could start imaging a target at the earliest with this date, but it might be more efficient to wait until the second date when you can have a maximum amount of imaging time for that target. Let's take a look at a couple of targets. NGC 5194 is the familiar M51. Now, also in this table is 5195, which is its companion galaxy over here. Obviously, I'm not going to go out and image NGC 5195 separate from NGC 5194. So that's one of the issues with this table, is I'm going to have a lot of stuff in here that, frankly, nobody's interested in observing, and that'll take time for me to weed those out. But now there's another one that I found by looking at this table. For example, this high score here, 0.88, that's NGC 5033, which actually looks like a fairly interesting spiral galaxy that I don't believe I have seen before, but yet I found through just looking at this peak observing score, saying that would be a target, whatever it is, that would be very easy, relatively easy, to acquire data on, because it's going to be near the zenith, and it's going to be up for a long period of time. And starting on March 24th would be a good time to go out and start imaging that target. Now, there are some very low scores down here. For example, 0.15 is the lowest in this little section of the data. And this is a pretty famous target. NGC 6523 is M8, or the Lagoon Nebula. For me, this is a difficult target to acquire enough imaging time on because of my complex horizon. And I'll show you what that looks like. First of all, let's take a look at how NGC 5033 looks on a altitude versus time plot. Once again, we have the month of the year, January through December. The green and the red represent the minimum and maximum altitudes the target reaches on a given day. So, for example, on February 1st, say, the target will just become visible as it passes over the fence line. And then, through the course of that night, it will reach up to a maximum altitude of a little over 85 degrees. Now, on that same day, this blue line represents the amount of observation time I have for that target on that day. So on February 1st, I will be able to see this target from here, read this over here. It's about 7 hours. So I'll have about 7 hours of observing time for that target. So that's not bad at all. Wouldn't hurt at all to go out and start imaging the target at that time. But the optimum time is right here, and that's where we get the peak score of 0.88, and that occurs on March 20th right here. And once we reach this, then we're getting the full range of minimum to maximum altitude, and we're seeing it for the longest period of time. But shortly after that, it seems to start clipping, my house starts clipping into the minimum altitude, so you see the observing score drop, and then presumably the time of day or time of night is shifting, so I'm losing some imaging hours, and then the imaging score or observation score really starts to drop, until finally it gets to 0 during about a 2-week period in October, when I can't even see the target because it doesn't rise above what looks like my fence line here. Now, here's NGC 6523, or the Lagoon Nebula. In this case, this target is barely visible at all. First of all, I can't see it from about the first week in November all the way up through the last week in March. So after that, I can only see it for a short period of time, as the minimum altitude is dictated by the houses down the street. Maybe my house, the houses down the street. It rises above the house line, the roof line, and then falls back down below the roof line on its way back down and setting. So here, it's not an optimal time to image this target at all. There's just a very small time period when I can see the target. It's not until roughly mid-June that I get the maximum observing time, which is limited to around a little over 4 hours, I believe. And it's just visible above the fence line. It gets up to a maximum altitude of about 33 degrees or so, and I've got to catch it a little bit at a time on successive days, but it certainly is a worthy target, and I certainly do want to try to take a picture of it. This just tells me that on June 18th, I need to start paying attention to this target and start capturing some data, because I'm going to lose it over the next 4 to 6 months. And then it'll start sinking again. So this is the kind of data that I'm getting out of the program. it's kind of useful. I hope it will be useful in planning imaging sessions going forward. So what have I found? Well, in running the program, I've gone through all the DSO catalogs that I can find and basically have come up with about 556 DSOs that are visible for more than 4 hours and reach a minimum altitude of 30 degrees. Now, as we saw in that list, not all of the DSOs are going to be worthy of imaging. Some of them, like the M51 case, it's just a companion galaxy and that's not a separate target. Other targets will not be, once I study them, pull up the name, they won't be worth imaging either. But at least this is a start. This tells me that at least I can see the target for long enough to image it. I then have to go through and actually look up the targets that I might be interested in, perhaps starting with the known targets that I'm interested in, or looking at the imaging score like I found that NGC 5033. This plot shows a breakdown of the DSOs that are visible from my backyard with my horizon, and it shows the type, nebula versus galaxy, and the corresponding imaging or observing score range. So from point 1 to point 2, which is where the Lagoon Nebula is, it's one of these 32 nebula targets that are visible, but only for a short period of time for me, given my complex horizon. Fortunately for me, there are many, perhaps most of the DSOs that I can see are observable for a long period of time, and there are roughly an equal number of nebula targets and galaxy targets in this range. So most of these 556 deep sky objects are visible for a long period of time. Well, this little study has given me at least some insight into the number of deep sky objects that are available for decent imaging. I just need to stop talking and get on to imaging. See you later, guys.